This is basically my costume for Purim. Yeah, so in honor of the Purim holiday, which is today, I'm wearing this ridiculous hat.
I thought it was because it's so sunny and hot here in Vienna that you needed a hat.
Yeah, in Israel it would be called extremely cold winter day. But
So we will have in a month, we will have Easter, but today we can say Happy Easter.
Happy Easter, yeah. Yeah, something like this.
All right, so Yair's going to give a talk now. Let me sit down and shut up. He's going to talk about partial strong compactness.
Yes.
Please, Yair.
Thank you. Okay. So thank you very much, and I'm hoping that the hat will not be too destructive. But let me see. So what I want to talk about today is basically about strongly compact cardinals and local versions of this concept. So I will start by discussing some well-known and classical things about global strong compactness. Basically, global strong compactness has various of equivalent definitions. I will talk only about a few of them, and then I will ask about how this equivalence localizes. So for example, we will have a definition using some compactness of the logic L kappa kappa and a definition using the existence of fine ultrafilters, and we will ask about their connection. Then we will go deeper to really the local instances of this strong compactness, and we will talk about equivalence and some well-known, some less known. We will discuss how they are related to existence of certain elementary embeddings. This will give us Taylor of squares, and from Taylor of square we will give an improved lower bounds for some strong compactness principles. Okay, so let's start with the beginning. So we have this, the first infinite cardinal Aleph 0. Aleph 0 has various of what we call compactness phenomena. For example, and basically when we go, or when historically people went to define things like strongly compact cardinals, they were looking at the properties of Aleph 0 and try to generalize them. So let's start with some really well-known properties of Aleph 0. So the ultrafilter lemma, it is basically a property of the first infinite cardinal. So what the ultrafilter lemma says? It says every filter, which means a collection of sets which are basically closed and subsets, supersets, can be extended to an ultrafilter due to Tarski probably. Maybe equivalent to this is the compactness theorem. And I'm saying maybe because when we look at the arguments going from the ultrafilter lemma to the compactness theorem or vice versa, there is some shift in the cardinality of the objects that we are considering. So let me try to make it more precise. Okay, so if one wants to prove the ultrafilter lemma using compactness, then there is a straightforward way. We say let F be a filter on some set X. We want to find an ultrafilter U extending F we are going to do is we want to use compactness. So what we are going to do, we are going to define a constant for every subset of X, and we try to basically realize some theory. So for each Y subset of X, define a constant C of Y, and we also want some unary predicate. So we have an unary predicate, let's call it U, and we would like to basically extend the theory. So find a model to some theory that looks basically like this. Well, U of Cy for every Y in F. So this means that we will get a subset of the power set of X extending this F. We will want something like U of Cy1 and U of Cy2 implies U of C of the intersection, right? And we will also want something like for every set, either it or its complement is in the ultrafilter. So for every Y, U of Cy, let's say, or U of C, the complement of Y. Yeah, and we will probably also want that the empty set is not fair, right? So we have some collection of sentences that are clearly finitely, every finite subset of it is consistent. We actually have a model for it, which is basically taking this finite set of subsets of X that appear in this collection, closing them under, let's say, intersection and complements, and asking which one of them is in F. We'll have the minimal one. Take even a principal ultrafilter on some of the elements of this intersection of all the elements in F, and this will work. Okay, so by compactness, we actually have a model for the whole theory. The whole theory, since we have this part here, we'll decide on actually an ultrafilter on X. Now, how many sentences did we have as the size of P of X, 2 to the size of X, which is essentially the size of a filter, right? Okay, if you want the other direction, and we are going through the, let's call it the naive version, which is usually attributed to Shelach. So we are going to say the following thing. In order to prove the compactness theorem from the ultrafilter lemma, we are going to say, well, take an ultrafilter extending the following filter, the collection of all Y that contains some A, Y is a finite subset of our collection of sentences T, where A itself is a finite subset of T. So basically, I'm going to look at the cones of all finite sets. But you just gave this
lecture this morning.
this morning, really. So why did you erase the board? On this one. So I should have asked you not to erase the board. So now I just have to rewrite it. Such a waste of chalk. So, okay, so we take an ultrafilter extending this filter of cones around finite subsets of the theory. And now we are going to say, okay, so let's call this ultrafilter U. Now, for every A, which is a finite collection of sentences, there is a model, let's call it M of A, which is basically a model of A. And now we're just going to take the ultra power. And by our choice of ultrafilter, this is going to be a model of T. Okay. Now there is something not quite right with this.
You think this is due to Shalom?
This, I think so, yes.
Surely this is older than.
I don't know. It's
Look, not everything is due to Shalom.
not everything. Even though guessing that something is due to Shalach is, a good approximation of the truth. Maybe Levi, I don't know. Anyway, there is something in this proof which is, let's say, a bit inaccurate in the following sense. So in order to deal with a theory with a size of T many sentences, we basically had to create an object of size 2 to the size of T, which is the ultrafilter. And then when we go back to the models, well, basically we know that, again, we can find a model of size, again, the size of T. So we go through a larger object, and in the context of ZF, for example, we go through really a stronger choice principle in order to prove this. And of course, there is a proof without going through this larger ultrafilter. And in some sense, what I'm going to do here in the context of strong compactness is something similar. Okay, so let's go to strong compactness. So a cardinal kappa is strongly compact if every kappa complete filter can be extended to a kappa complete ultrafilter. This is just a generalization of the ultrafilter lemma. And basically using exactly the same thing, we can say that some generalization of the compactness properties of aleph 0 also follow immediately. And we are going to talk about L kappa kappa, the logic L kappa kappa. So what is L kappa kappa? We basically take the first order logic, but instead of requiring, we extend it in the sense that we allow to take disjunctions and conjunctions of less than kappa many formulas, as well as quantify over less than kappa many variables at each time. So we have much more, the logic is much richer. It can express more things. It can express well-orderedness for kappa uncountable and so forth. And L aleph 0 is the first order logic. Okay, so we have basically the compactness theorem for L kappa kappa, and this is equivalent by basically this argument to the filter extension property for kappa complete filters. Okay. Yeah. Okay. Going slightly ahead in time, at some point in history, we started to analyze using elementary embeddings basically, and specific type of ultrafilters. This always goes together. So, so this is let's say the modern definition. A cardinal kappa is lambda strongly compact if there is a kappa complete fine ultrafilter on P kappa lambda. So it is lambda strong compact if there is one ultrafilter witnessing it. What is a fine ultrafilter? So this is basically a filter of this form. So let me just write it down. So an ultrafilter U on P kappa lambda is fine if and only if for every A in P kappa lambda, the set of all x's in P kappa lambda containing A is in U. Okay. Same for filter, basically. Okay. Now, when we think about ultra powers using a fine kappa complete ultrafilter, we are going to get an elementary embedding like in free. So when we just, this is an easy exercise. Once we take the ultra power using a fine kappa complete ultrafilter, then we're going to get elementary embedding from V to M, which is actually going to be a transitive model if kappa is uncountable, with critical point kappa. And there is some set which is basically the ID, the identity function, that's going to contain all the pointwise images of the ordinals up to lambda. And it's going to have size less than J of kappa. Okay. Now this means, if we think about this, this means that J of kappa is going to be a discontinuity point of J. J of lambda, sorry. J of lambda is going to be a discontinuity point of J. So the elements J image of lambda is going up to J of lambda, but not meeting it. We have the supremum of this set, which will have a cofinality less than J of kappa. So clearly it's going to be less than J of lambda. The more non-trivial direction is the other direction. So this is due to Gödel, which says that if we have this type of discontinuity for every regular cardinal between kappa and lambda, then kappa is lambda strongly compact. Okay, so having discontinuity at elementary embeddings is the same as having a very specific type of ultrafilter. Okay. Okay. So far everything is okay. Now this previous theorem actually gave us a level-by-level equivalence of some form of strong compactness. So we had the definition of strong compactness using fine ultrafilters, or equivalently elementary embeddings, where the image, pointwise image of lambda is bounded by some small set, or embeddings with some discontinuity. But if you go back in time to the historical definitions using L kappa kappa compactness or extensions of filters, then things are much less clear. Obviously, every L kappa compactness for L kappa kappa theory of size kappa is just weakly compact. It just means that kappa is weakly compact. Now, if kappa is strongly compact, it is in particular measurable. So we don't have a place in the hierarchy for this type of compactness principle. And I will try to convince you that this is actually, we can say something even stronger. I mean, we can say that L kappa kappa compactness for various sizes of theories are not exactly aligned with the existence of fine ultrafilters. They are somewhere in between. Okay. Okay, so we need some way to express this thing. So, okay, let's fix two cardinals, kappa and lambda, and we say that the L kappa kappa compactness holds for languages of size kappa if every L kappa kappa theory T over a language with at most lambda many symbols. For this we have the compactness, so it is consistent if and only if every fragment of it of size at most kappa, strictly less than kappa, sorry, is consistent. Okay. Okay, so this is, let's focus for a moment in this principle. And let's observe that we have an elementary embedding characterization of this principle, similarly to the one that we have for weak compactness. Okay, so the following should be equivalent. L kappa kappa compactness for languages of size lambda, and the second assertion is we have for every, so we don't really have a characterization in terms of elementary embeddings of V, the whole set theoretic universe. But we do have it in sense of fragments of it, which makes sense as we basically we need to also be able to catch the case of lambda equals kappa, which is just weakly compact. Okay, so the elementary embedding that we are going to get is the following: for every model, transitive model of size lambda, which is closed under less than kappa sequences, this is one point in which we actually need the fact that lambda is lambda to the less than kappa. There is a transitive model N, an elementary embedding with critical point kappa between M and N, and we have something of some weak sense. We have also strong compactness for this embedding. So we can think about this as J image of lambda, basically, right? Because M has size lambda, and we can just have a function inside M enumerating it itself. So basically, J image of lambda is covered by some small set in N. Okay? How do we do this?
So what is you replace your embedding in V by an embedding in the small size lambda model?
Yeah, yeah.
As you get from measurable to weak compact by replacing V by size kappa.
True, but note that for strongly compact cardinals, we have no reflections at all, right? Strongly compact cardinal, the first strongly compact cardinal may be the first measurable. This is a well-known theorem of Megiddo. So below a cardinal which is kappa plus 100 strongly compact, there might be no cardinal rho which is rho plus 7 strongly compact, right? So here we don't really have a reflection, so we can't apply reflection in order to get compactness is strong at weaker cardinals, but still we have something. Okay, so let me just sketch the argument because it is simple and short. So we basically want to apply, let's think about the forward direction. So we want to apply L kappa kappa compactness and get an elementary embedding. How do we do this? So let's M be a model, some set theory, a transitive model, closed under less than kappa sequences, size lambda. Maybe I didn't, should have written it. Yeah, I probably need also to assume that lambda is a subset of M, I guess. Otherwise I just need to extend it. Okay, how do I define N? How do I find N? So what I want to say is I'm going to apply compactness on the following theory. So for each x in M, define a constant C of x. This is basically going to be realized as J of x. Also, we will have a constant S. Well, realizing this covering set S, small set S. Okay, and we will have and one last additional constant D, which will be basically an ordinal between kappa and J of kappa. Okay, so this should be a set that contains J image of M. This should be basically J of x, and this should be basically kappa. Okay. So now let's see what application of L kappa kappa compactness we are going to do. So let's write the following sentences. So first of all, for every L kappa kappa sentence which is true in M, okay, so we have some phi with some parameters a0 up to a n minus 1, such as M thinks that this is true. So we want to include phi of basically C, a0 up to C, an minus 1, in our collection T. Okay, so first of all, we just put the elementary diagram of M inside the L kappa kappa elementary diagram, so it will in particular be a well-founded model. Okay, also we want to make sure that we will get a non-trivial elementary embedding. So for every alpha below kappa, we will require that C of alpha is strictly less than D. For while, let's write it like this, D itself will be strictly less than C of kappa. Okay, so this is, I mean, for each one of them separately. Yeah. We have kappa many different sentences that we are going to include in T in this one. And the last thing is we want to deal with this S. So basically we are going to say for every x in M, include the following: C of x is in S, in T. And we want to make sure that it's going to be realized as some small set. So we want also to include S has cardinality strictly less than C of kappa to be in T. Now, let's verify that this is less than kappa consistent. So if I'm going to take less than kappa many sentences in this collection T, then I'm going to mention only a few elements of M, basically less than kappa many elements of M. So here I'm going to mention less than kappa many ordinals. Here I'm going to mention less than kappa many elements, also here. So eventually I'm going to have some small collection of elements that I need to worry about. So for every T prime subset of T of small cardinality, there is a small set, some B, subset of M. Size less than kappa, of elements that appear. Okay. So now, how do I find this model witnessing the consistency of all these things, basically it's going to be just M, right? So M will witness the consistency of all these diagrams when I realize D as some ordinal that didn't appear and S as B. So M, some gamma which is sufficiently large, and B will be a model of this type. Okay, so well, let's say larger than the supremum of B intersection kappa. This is surely enough. Okay, so it is easy to find a model for this theory T prime, so we know that by compactness we will have a model for the whole thing. But the whole thing is going to be a well-founded model. And collapsing it, we will exactly get this N that we want. Okay, so is it clear? We write it down.
You just want elementary. You need the L kappa kappa only for the well-foundedness.
I need L kappa kappa and even less for the well-foundedness, yes.
You need L kappa omega 1. I mean, you need a single sentence from L kappa omega 1.
L omega 1 omega 1.
L omega 1 omega 1.
But the point in which I actually use some strength of this L kappa kappa is when I make sure that the critical point of J is actually kappa. So in order to make sure that I didn't introduce a new ordinal smaller than kappa, I actually need something like L kappa omega or something like this. So, which is essentially the same thing. Compactness for this one and compactness for that one is basically the same thing. Okay, so let me move on. Okay. Okay, let's go to the filter extension property. Right, basically the original definition of Tarski. Okay, so let's take two cardinals kappa and lambda. We said that a kappa filter extension property holds for lambda if and only if every kappa complete filter on lambda can be extended to a kappa complete ultrafilter. Now there is something a bit misleading with this terminology, because talking about extending filters on lambda, we are basically talking about objects of size 2 to the lambda. Now, let me just mention that it is classically known that if we restrict ourselves to filters which are generated by lambda many sets, then this is just the same as lambda strongly compact. Okay? But here we are saying something which is a bit more delicate. So we are talking about every filter on lambda. So we have really a lot. And we are talking. Now it is a bit less obvious how to get an elementary embedding characterization of this property. And indeed, it was a question of Mitchell. So Mitchell asked, well, it was really in the beginning of the inner model theory. So now this question seems to be a bit silly, but back in the day it was very it made a lot of sense. So Mitchell asked the following question: let's take the kappa which is sufficiently large, strongly compact cardinal, super compact cardinal, whatever. Now work in L of U. L of U is the core model for sequences of measures. So basically, now it is called the core model below of kappa equals kappa double plus. Is it true that kappa has the kappa filter extension property there? So naively speaking, this makes a lot of sense, because the filter extension property basically says that some ultrafilters on kappa, complete ultrafilters on kappa exist. Now, L of U should catch those ultrafilters, right? L of U basically catches many normal measures on kappa. It wasn't long, I don't it wasn't long until Gitik gave the first negative answer for this question. So what Gitik shows is that in 1993 is that if we have the kappa filter extension property for kappa, then there is an inner model with a strong cardinal. I think that I'm actually going to give a sketch of the argument, and lately he improved this. If the kappa filter extension holds for kappa, then there is an inner model with a Woodin cardinal. Now, later in this talk, I'm going to improve this result further, but I think that those two results are extremely interesting by themselves because they show, well, the proof shows that the kappa filter extension property, even for quite definable filters, has a significant consistency strength. Okay. So both of the arguments are based on the weak covering lemma. So what is the weak covering lemma? So if we walk over a core model which is sufficiently small, let's say below 1 Woodin cardinal, then we know that the core model approximates the universe quite well. I won't go into the exact details of what does it mean. So usually we say that it computes successors of singular cardinals correctly. Here the usage is slightly more delicate. It's about how elementary embeddings of the core model K to a transitive model are basically comes from K itself. But let's see. But still, we can say a few things about the ideas of the argument. So the first thing, in order to get an inner model with a strong cardinal, what basically Gitik showed is that if there is no inner model for a strong cardinal, then every kappa compact, yeah. So kappa compact means that the kappa filter extension property holds for kappa. So it is tall. A tall cardinal is just the following thing. A cardinal kappa is tall if for every lambda there is an elementary embedding J from V to M, such that M is closed under kappa sequences. This is basically the non-trivial part, and J of kappa is large. So removing this assumption that M is closed under kappa sequences, it would be just a measurable cardinal. You can just iterate a measure long enough and make J of kappa as large as we want. But but assuming that M is closed under kappa sequences actually make it a very, very strong. Not a strong cardinal, but in an inner model there is a strong cardinal. Kappa is going to be a strong cardinal in an inner model. So the first proof of Gitik basically shows that if kappa is not tall, then there is a way to combine using the kappa compactness, basically using this kappa filter extension property, there's a way to combine the filters on kappa in order to get a longer extender, making J of kappa larger while keeping the closure under kappa sequences. This is a very nice argument. The second one, the more recent one, is approaching the problem from a different angle gets also a stronger result. So the idea is to try to extend a very specific kappa complete filter. So the kappa complete filter that we are trying to extend is the following. It's a very interesting one. So we take the club filter in the core model K on kappa, but we restrict it to some set which is stationary in kappa, but not necessarily stationary in V. So we are going to talk about, let's say, the set of all ordinals of countable cofinality in the core model K. Now it is not trivial, but not extremely difficult to see that it is consistent with respect to not extremely large cardinals, that this set is simply non-stationary. Nevertheless, the club filter of K restricted to this set, assuming that there is no model with a Woodin cardinal, is always kappa complete filter. This is a usage of the weak covering lemma, which basically uses the fact that kappa plus is computed correctly in V. Okay, now if we try to extend this filter to a kappa complete ultrafilter, then we are going to get, well, we are going to get an elementary embedding by the ultra power. It's going to be basically an elementary embedding from the core model K to some, the core model K of some model N. And again, by the application of another version of the weak covering lemma, we can actually say that this embedding has a very specific type. It's not really important what exactly a branch for an iteration tree means, but for those of you that knows, it helps, and for those of you that doesn't know, it just means that we apply some extenders from K in some order, or some of them are coming from different models, but it doesn't really matter. We have a list of critical points in this process, and this list is increasing, and it contains only regular cardinals from the point of view of K.
Isn't this, by the way, a result of Ralph?
Yes, it is. Yes. I mean, when we talk about the weak covering lemma, then, it's like a zoo of results. But all of them are in the same theme. So I think that Ralph's result is the strongest that we know of, right?
Yeah, I mean, it's basically the statement of the first line.
Yeah.
Exactly.
Yeah, it is. It is. Yeah. This is due to Ralph. Yeah. Gitik has the same result, but below a strong cardinal or something like this, which is weaker because you don't need an iteration tree. Anyway, let's look at the identity function, what ordinal it represents under this ultrafilter U. So it will represent something singular. So it's not any one of those K of kappa alphas. Now it basically means that there is some function from K written to J of F, such a J of F applied on kappa of alpha is going past delta. This is a standard trick. Every ordinal is represented in this way, but in order to say this, we need to assume some assumption about the length of the extenders. So the extenders are not too long. Okay. We basically don't have a super strong type of extenders. Anyway, once we have this, we have a club. Oh, and here is another type. Oh, sorry. Yeah. So we have a club E. The club E is just the closure points of F. Okay, clearly a club, clearly in K. But also clearly delta is not in J of E. Right? Because delta itself is not a closure point of F. Okay, so this is a contradiction. So it means that there is a quite definable filter, assuming the weak covering lemma, which cannot be extended. And this is very interesting. Okay. This is a very small remark, so let's assume for a moment that for some reason we managed to get the weak covering lemma for some inner model larger with a super strong cardinal. So super strong basically means that we have an embedding which obtains some closure properties with respect to V of J of kappa. Okay, so we need slightly more than this, and it is not difficult to see that once we have this, we actually can extend the club filter restricted to K to S kappa omega. Okay, so this is a nice exercise because at some point you might ask, okay, so So extending every kappa complete filter on kappa is clearly possible, assuming something like kappa plus strongly compact. Well, if we believe the inner model theorists, then it should be possible in an inner model of kappa which is kappa plus super compact. But can we reduce this assumption? So for some specific type of filters, like the club filter restricted to some stationary set, we can reduce it to something lower. But how? Okay, so the consistency strength, the exact consistency strength there is an interesting problem. Let me say more than this. If you are actually only interested in stationary sets from the ground model, then Gitik has another result, which I didn't quote, saying that you can actually get it assuming something quite weak, below of kappa equals kappa double plus. Okay? So the question of kappa filter extension property for quite a definable filters behave differently than that general one. And okay, so the next step will be to get an equivalence between the kappa filter extension property for kappa or for lambda to some compactness of L kappa kappa. Okay, so this is the statement. The following are equivalent for a cardinal lambda, which is lambda to the less than kappa. We have the kappa filter extension property for lambda, and we have L kappa kappa compactness for languages of size 2 to the lambda. Okay. Okay, so this is the statement of the lemma. Once we have this, we will be really a few steps away from improving the consistency strength quite a bit. One direction is clear. So which direction is clear? So from this to this is the clear direction. If we have L kappa kappa compactness for languages of size 2 to the kappa, then we can basically just plug in all the subsets of lambda as constants and apply the argument that I gave in the beginning for getting the ultrafilter lemma from compactness. So this direction is clear. Yeah, so this is true. One direction is clear. The other direction is slightly more subtle. So for the next direction, we actually need something which is called kappa-independent families. So this is a well-known combinatorial objects, which were, well, let me say, Hausdorff proved it for kappa equals lambda equals aleph 0, but exactly the same proof works for general kappa and lambda. So let me say that this is a theorem of Hausdorff. So the theorem is like this. If we have a cardinal lambda, and lambda to the less than kappa is lambda, then we have a kappa-independent family of subsets of lambda. So what does it mean? It means that whenever I take a Boolean combination of length less than kappa of sets from this family I, then I'm going to get a non-empty set. Basically, I'm going to get a set of size lambda even. And the size of this independent family is the maximal possible size, 2 to the lambda. Okay, so this is a really well-known result in the context of the continuum. Right? There is an independent family of the continuum of size continuum. This is why when we talk about the characteristic of the continuum and we talk about the minimal size of the maximal independent family of the continuum, it might be below the continuum, but there is always one of size continuum. And this generalized to every uncountable cardinal. So we have a kappa independent family of size 2 to the lambda. Okay. Okay, let's use it. So fix such a kappa independent subset of P with a lambda. Now, on the other hand, we have some theory. We have some T, a theory in L kappa kappa with 2 to the lambda many symbols, 2 to the lambda many constants. So basically, we have 2 to the lambda many possible sentences in this theory. And we want to get basically, we want to extend it to a maximal consistent theory. We want to decide every sentence if it is true or false in some sense. We don't really need the quantifiers, right? This is the standard trick in logic. We can just add constants for every quantifier, for every existential quantifier. We just add a constant witnessing it, and we and we're fine with this. Okay. Now, so we need to basically realize some very concrete sentences. So basically, there are L kappa omega sentences. Okay. So what we are going to do, we are going to embed this problem into a problem of extending a filter. How are we going to do this? So basically, we have some sentence phi, some atomic formula phi. Now, I want to attach to this phi a member of I. A different member for every formula. And now I'm basically getting an embedding from the Boolean algebra of the sentences to the Boolean algebra of P of lambda, right? I can extend it. So this is for atomic formula. And I can extend it. So if I have a conjunction of less than kappa many formulas, I'm going to send it basically to the intersection of those sets. And if I have negation, I'm going to send it to the complement. Okay, so I'm embedding basically the Boolean algebra of formulas into the Boolean algebra of sets, of subset of lambda. And okay, and now let's see what should we get. So I'm just adding constants. I'm doing the Henkin construction. So with our class of generality, I don't have constants. I just extend the language, adding it must 2 to the lambda many constants, and I can assume that I don't have any quantifiers. Okay.
But you want the Henkin sentences to be satisfied also?
Yeah, of course. This is for everything's extended theory. After we added the constants and realized it. Sure. So we have 2 to the lambda many things to worry about, and we have basically less than kappa many steps. Each one of them adding basically 2 to the lambda many constants. So we can certainly do this, and we don't need to worry about this part. Is it okay?
You still have the Henkin sentences which have quantifiers in them.
Yeah, so they will, okay, yeah. But they won't really matter for me when I'm trying to find a model, right? Basically, I'm trying to find a model for T. In order to find a model for T, I just need to know what are the relations between every two constants, right? So basically, I just need to realize, like, so when I do the Henkin construction, what I'm going to get is some formulas that look like, is it true that f of c of x is c of y, right? And things like this. So is it true that some relation of c of x, c of y holds? Those are my atomic formulas.
So the model you construct is the constants as its universe.
Yes, and exactly. So
Yes, and then every first sentence is just true if it's true for constants, yes.
yes, yeah. My model is just going to be the constants. I don't have anything else in the model. Okay, this is the Hankin construction, and this also should ring a bell because right in the beginning of the talk, I said that the ultrafilter proof of the compactness theorem is wasteful, right? Because it was using something larger, and we know that there is a non-wasteful proof of the compactness theorem, which is the Hankin construction, basically, right? So in some sense, I have to use the Hankin construction here in order to avoid the wastefulness.
In the classical proof, you want to have a complete theory, so you need an ultrafilter.
Yes. So here I will also use.
Well, yeah, okay. Oh, I see. You only need the ultrafilter on you need choice on the countable set.
Yeah, which is right. Okay. So there is a distinction here. We basically have an ultrafilter on some Boolean algebra, which is much smaller than the full power set. Yes. Okay, so we basically need just to embed the atomic formulas and extend the embedding, but we need to make sure that this extension makes sense. So basically, we need to make sure that if we have a consistent collection of formulas, of sentences, then we are not accidentally sending them to the empty set. Okay? So for every, and now the main part of this lemma is that this is by induction. Since I is independent, it's kappa independent, for every collection of less than kappa formulas which is consistent, the image is non-empty. Okay, this is really a routine verification. So basically I'm going to say there is a way to realize this. This basically means that I have in this collection of less than kappa many formulas, I have less than kappa many atomic formulas that I need to decide. The fact that they are consistent means that I have one assignment, at least one assignment on this collection which actually makes sense. And it is not hard to see that this assignment basically gives me exactly a set of the form intersection of A of phi for every phi which is true minus intersection of A of phi for every phi which is false. And this is always non-empty. Okay, false in this assignment.
What does it have to do with collections of formulas which are consistent?
So I need to have an assignment, basically just a propositional consistency assumption. So I have less than kappa many formulas, basically just like propositional ones. I just have truth values, and I need to know that the conjunction of all of them is consistent, right? Is not. I assume that it is consistent. What does it mean that it is consistent? It means that it has an assignment. I have an assignment for each one of these atomic formulas that appear during this process, assigning the truth value of it. And this assignment makes the whole collection true. Okay, this is basically the definition of consistency of collection of formulas which are just positional one. Okay, so using this assignment, I'm going to get, if you think about this, some subset of the intersection of A of phi for phi in the collection, and this subset is of the form intersection of some elements of I minus intersection a union of other elements of I, then this is going to be large. Okay. So let's use now the fact that we can extend this filter to a kappa complete ultrafilter. Now we basically decide the true value of every atomic formula. It is either A of phi is in the ultrafilter or A of negation of phi is in the ultrafilter. So we have a maximal consistent theory. Okay, and since the ultrafilter is kappa complete, it will respect L kappa kappa sentences. Okay, so this is it. It's okay? Sort of? Is it all? Okay. What do we get from this? Okay, so in order to derive a consistency strength from various elementary embeddings, we can use square principles. So squares are basically an anti-compactness principles. Let's start with the definition. So I'm going to use the definition of Todorchevich. Okay, let lambda be a regular cardinal. A square of lambda with this form, lambda is inside the parentheses, is a sequence of basically closed sets, C alpha, alpha less than lambda, limit ordinals. If the following property, C of alpha is a subset of alpha, which is closed and unbounded in alpha. For alpha, which is of uncountable cofinality, I can say that it is a club in alpha. And an accumulation point of C of alpha, C of beta is basically just the restriction of C of alpha to beta. Everything here so far will work perfectly fine if C of alpha equals alpha. But one additional thing, which is the main point of this object, is that I don't have any way to extend this square even by one additional point. So I don't have any club D that can be C of lambda. So what does it mean that it can be C of lambda? It means that I don't have any club D such that for every beta, which is an accumulation point of D, C beta is actually the intersection beta. So there is no way to extend the sequence even by one additional point and maintain its properties. Okay? So this is an anti-compactness principle in the following sense. We have this property that every initial segment of the square can be extended, and it simply fails at the top level. And indeed, if kappa is weakly compact, then square of kappa fails. The other direction in some sense also holds. If square of kappa fails, then kappa is weakly compact in L, in the constructible universe. Also in K, I guess. Yeah, and if kappa is strongly compact, then above its squares fail everywhere. Okay. Okay. So those principles give us some way of measuring failure of compactness in some sense. So in presence of compactness, those principles fail. Okay. Now we can get the following interesting lemma. So if we have kappa which has the kappa filter extension property, so every kappa complete filter on P of kappa can be extended, then square of kappa plus fails. Basically, square of lambda for every lambda below 2 to the kappa will fail, including 2 to the kappa itself. Why? Maybe I should write it down. So I'm going to use the characterization using elementary embeddings of the L kappa kappa compactness. Okay, so it is, I didn't write it through. Okay. So remember, we know that kappa filter extension property is equivalent to L kappa kappa compactness. For basically 2 to the kappa, for sentences of size, languages of size 2 to the kappa, which is equivalent to the following statement. For every M transitive, which is closed under less than kappa sequences, there is some nj, such that J is an elementary embedding from M to N. The critical point of J is kappa, and the J image of 2 to the kappa is small. It's covered by set S in N, which is size less than J of kappa. Okay? Let's assume for simplicity that 2 to the kappa is simply kappa plus, because clearly this property is downwards absolute. So if we so it's not about term. If we take something which is smaller than 2 to the kappa, clearly it will hold for it as well. So let's do this for kappa plus. Okay. How do we do this? So let's assume that there is a square sequence. Assume that C alpha alpha less than kappa plus is a square of kappa plus sequence. Okay, let's call it call C. Okay, we will take a model M of size kappa plus that contains C. Some elementary substructure of something large. M has size kappa plus, and kappa plus is contained in it. Okay? Now, M is transitive, M is closed under less than kappa sequences. Now let's apply the elementary embedding. So we have some J N transitive, and J image of kappa plus is going to be small. So in particular, when I'm going to take the supremum of J image of kappa plus, I'm going to claim that it is strictly smaller than J of kappa plus. Right, the cofinality of this object from the point of view of N is at most the size of this covering set, which is less than J of kappa, while the cofinality of this ordinal from the point of view of N is J of kappa plus. Okay, so call this delta. Now, J of C at the point delta makes sense. C is a sequence of size kappa plus, so J of C is a sequence of size J of kappa plus, so it has this element delta, which is basically this supremum of J image of kappa plus. Call it D tilde. Okay. Now, J image of kappa plus is a quite closed set. It's less than kappa closed. This follows from the fact that the critical point of J is kappa. So, the intersection of J image of kappa plus with the accumulation point of D tilde is large. Let's say the supremum of this is delta. Okay. Okay, and now we are almost done. So take let's take all alphas such that J of alpha is in the accumulation point of D tilde. And now I claim that C of alpha, let's call it I. So for every I less than beta, alpha less than beta in I, C of alpha is an initial segment of C of beta, because J of C of alpha is an initial segment of D and also J of C of beta. It means that now we have the real thread. D is simply the union of C alpha alpha in I. It's clearly a thread. Okay. So we get that the kappa filter extension property implies failure of square not at kappa but at kappa plus. Well, also at kappa, of course, because it means that kappa is measurable. And it is an easy, well, I wrote it, right? If kappa is even weakly compact, then square of kappa fails. We have failure of square of kappa at kappa and square of kappa and also square of kappa plus. Yes, makes sense. So how strong is the failure of square of kappa plus? Well, by itself is not that strong, right? If you just, this is an easy exercise. If we take a weakly compact cardinal and collapse it to be the successor of kappa, then we will have square of kappa plus. But in order to maintain square of kappa, we actually need a lot more. And this is a theorem of Jensen, Schimmerling, Schindler, and Steele. It means that if we have a cardinal larger than aleph 2, which is, I didn't write it, sigma closed, okay? And we have the failure of square of kappa and even a weaker version of square of kappa plus, weaker version of the failure of square of kappa plus. Then already we have an inner model with a lot of large cardinals. Basically, it's the largest inner model in which we actually can have a proper inner model theory without any iteration assumption. So class many strong cardinals, class many Woodin cardinals. And once we insert many iteration assumption, many iteration hypotheses, then we get more. So where should we aim to? So basically it's above all these models with many Woodin cardinals. So we are going to aim to subcompact cardinals. Okay. So let's go back a bit. So when we talked about, when we discussed the compactness properties of aleph 0 that we used in order to define strongly compact cardinals, we actually missed one. We went over your course in logic, and we missed one fundamental theorem, which is the Levenheim-Skolem theorem.
Guess what? I heard that today.
Great. Great. So the Levenheim-Skolem theorem says the following thing. If we have a model, then there is a countable elementary substructure of this model. We have models of any size that we want. But if we go to extend it, we want to generalize it and to get a proper large cardinal axiom, then it is a bit tricky. But we can just say a larger elementary substructure because this already exists. So one possibility is to use stronger logics. So Megiddo showed in his PhD thesis, I think, that the following is equivalent to supercompactness. Yes, we went to supercompactness at last. So kappa is supercompact if and only if the following holds. For every lambda above kappa, we have some lambda bar below kappa, and an elementary embedding from v lambda bar to v lambda, such that the critical point of this elementary embedding goes to kappa. So kappa is not the critical point of the embedding, but rather the image of the critical point of the embedding. This is a bit of shift of the point of view when you think about the largeness of kappa. Okay. And this is also appear in this paper. This is equivalent to Levenheim-Skolem theorem for second order logic, or basically just for a logic which is strong enough in order to capture the notion of will is the power set. So it can capture all the power set of something. Okay? Localizing it, we get a very interesting notion of large cardinal started at Jensen for lambda equals kappa plus, but I think that he also meant to the general version, which is the following. So we said that a cardinal kappa is lambda subcompact. The subcompact is simply we found the lambda. If for every subset of H of lambda there is so we have some reflection of lambda bar below kappa bar below lambda bar, and A bar, which is a subset of H lambda bar, and an elementary embedding like this. So this is a bit of localized version of Megidor's theorem. It's more precise in some sense. Okay. Now, if you have the continuum hypothesis at kappa, then it is easy to see that once we have a kappa which is kappa plus supercompact, then kappa is going to be basically also kappa plus subcompact, and this is going to reflect downwards. So subcompactness is strictly weaker than supercompactness at the same level. Okay. But we need even to tweak it a bit more. So I'm sorry about this, but we actually need to squeeze it a bit more. So we want to add additional assumption about the reflecting structure. So we focus on the case kappa plus, which is the interesting case. So we say that a cardinal kappa is kappa plus pi 1 1 subcompact, if not only that we have this embedding as we had before, J from H of kappa bar plus to H of kappa plus, reflecting some predicate on kappa plus. But we have one additional thing. This structure is slightly better than usual in the sense that if we specify some pi 1 1 sentence on H of kappa plus, so we're basically accessing something slightly larger. We're accessing some information of kappa plus, then this sentence will reflect to the lower model. Okay, this is a very interesting notion. Again, it is strictly below kappa plus supercompactness, but it is tightly connected to failure of squares at kappa plus. So this is really an easy exercise. If kappa is kappa plus pi 1 1 subcompact, then we have failure of square at kappa and kappa plus. Okay, this is the easy direction. The other direction, which is extremely difficult, and this is the theorem of Neyman and Steele, says the following. I don't think that I know exactly what weakly iterable pre-mouse means in this context, but under some assumption, some inner model theoretical assumption, if we have failure of square of successor cardinal, then we must have a pi 1 1 subcompact cardinal in the model. Okay, this is very interesting. So it means, in particular, just plug in the previous argument that we had so far to this theorem of Neyman and Steele. If which itself a weakly iterable pre-mouse, if we work inside some inner model theoretical universe, and we have a cardinal kappa which has the kappa filter extension property, then kappa is kappa plus pi 1 1 subcompact.
Yeah, but are there any weakly iterable pre-mouse with such a property?
Of course that it is unknown.
This is all.
This is open. This is open. This is, once we go past the, I think, the Woodin limit of Woodin cardinals, then everything is blurry. I mean, I'm not an inner model theoretical guy, but this is, yeah, I mean, this theorem is a theorem, it's a proper theorem. It might be empty. It might be vacuous, but it is a theorem. I mean, if you manage to, so it might mean two things. It might mean that once you have, which are both interesting, it might mean that there is a way to get weakly iterable pre-mouse at this level. And this means that at this level we will have equivalence of the kappa filter of this filter extension property and pi11 subcompactness. And it might mean another thing which is also interesting, which is that once you have some cardinal of the filter extension property in the universe, then no inner model which is weakly iterable can approximate it correctly. So it can't approximate kappa plus correctly. Both things are quite interesting. I mean, yes, okay. So, yeah, but here I'm writing if and only. So there is the second direction saying that if kappa is kappa plus pi11 subcompact, then actually the filter extension property holds for kappa. Yeah, this is again an easy exercise. Maybe I should actually do this, just in order to get one application of pi11 subcompactness in order to not leave it that vague. Okay. So let's say that we have kappa which is kappa plus pi11 subcompact. Okay. We want to show that every filter on kappa, every kappa complete filter on kappa can be extended. So let F be kappa complete filter, and let's assume towards a contradiction that it cannot be extended. Okay? What does it mean that it cannot be extended? It means that for every ultrafilter, either U is not kappa complete ultrafilter, or that there is some X in F which is not in U. This is a pi11 statement in the level of H of kappa plus. Yeah, here I am basically saying something about subset of H of kappa plus. So I am saying for every subset of H of kappa plus, something happens, and this is elementary. This is first order, sorry, at H of kappa plus. Okay? So applying this definition of pi11 subcompactness, we get the following. We get some kappa bar and F bar and embedding. And moreover, we may assume that this structure also witnesses the same pi11 sentence, which is basically saying that F bar cannot be extended to a kappa bar complete ultrafilter. Okay? But we actually know how to extend it, because look at J image of F bar. This is simply an element of H of kappa bar, H of kappa plus, sorry. Let's think about this for a moment. So this is an element of the size 2 to the kappa bar, right? Consists of subsets of kappa, basically. So so it is a member of H of kappa plus. But it is also contained in F, right? Every member of F bar will go to a member of F. So we can intersect it. So the intersection is a member of F, in particular non-empty. Take an element here and define an ultrafilter. Okay? So we define a U bar to be all the excess subsets of kappa bar such that A is in the image of axioms. This is clearly a kappa bar complete ultrafilter, contradicting our assumption. Okay, so we have a candidate, and we can conjecture, a bold conjecture, that this is an equiconsistency result. Okay, so if you have kappa such that kappa has a kappa filter extension property for kappa, then there is an inner model with some lambda, which is lambda plus pi over 1 subcompact. I mean, it might be not exactly the same kappa. We might have some small maps, and then we need to extend it. But basically, we'll have pi over 1 subcompact in the model. Okay. Any questions so far? I'm not sure if I want to go to the next part of the lecture. It is short, but maybe not sufficiently short. Okay. So what do you prefer? Should I?
What time is it?
We have like 8 minutes, I think.
8 minutes.
So what is the content of the next?
It's about the strong tree property and the ineffable tree property. And
That needs more than 8 minutes.
yeah.
It's a lot to, just defining them takes 8 minutes.
Well, defining the strong tree property doesn't take that long, but defining the ineffable tree property might take a bit longer. So let me stop here.
So Niemann was led to these reflecting subcompacts because of an extremely interesting theorem he proved. And I keep dreaming there'll be other theorems like this. But so far, there's only one theorem like this. And it's Woodin. The punchline of this theorem is that if you can force PFA with a proper forcing,
Yes.
then your ground model must have had
Strong
a
property.
subcompact.
Yeah.
Maybe even a reflecting subcompact.
But there is this theorem of Viala and Weiss.
Related to the BLI, I also, since this work I was doing wholly, I mean, Niemann was saying, it's a little more complicated than that. He was saying that if the ground model is somehow L-like,
Yes.
and by a proper forcing you produce a fragment, large enough fragment of DNA,
Yes.
then in the ground model you must have had a very large cardinal at the subcompact level of cardinal.
Yeah.
Of course, Foley and I filled the gap by showing that actually, if subcompacts are consistent, they're also consistent to exist in these L-like models. You needed a lot of L-like. You needed various forms of L-like reflection, compensation, acceptability.
Yeah.
And the L-like
Okay.
had a related result where they forget the L-like. They just said, if you can force it with, if you can force it, say, with covering properties, approximation properties.
Yes.
So the jury was, you call this like a quasi-lower bound. It doesn't say that you need the large cardinal, but you need it if you got your result by forcing of a certain property.
Yeah.
So one could dream that maybe you can reverse the extension property in this quasi.
So you can do a silly thing, I think. You can work in a model in which you have the square principles everywhere, except at some areas at the minimal large cardinal property.
Subcompacts start to trip up square principles.
Yes. So you can certainly have those kind of things. You can force them. You can force to have.
Niemann was using much more than square.
Yeah, but here, I mean, if you are interested only in the filter extension property, then basically it just reduces to squares which are sufficiently indestructible. So those things you can cheat your way through and say, if you, consistently, there is a model of GCH in which the places in which square fails are exactly the places which are predicted by some subcompact
Yes.
principle. And right, this might be even yours.
Yeah, well, Brooke Taylor and I have a paper on this.
Yes, okay, yeah.
Exactly what large cardinals do you need to defeat squares?
Yes, yes. So if you start with such a model and you try to force some cardinal to be with the filter extension property, then you must have started with pi11 subcompact, right? But just by the argument with the squares. But hopefully you can do better than this. I mean, hopefully you can just say, I mean, this is the dream to be able to say just from the field of squares at two successive cardinals, let's say above the continuum, to get very large cardinals. Right? At the continuum, it's still you can do something slightly better.
But
Yeah.
in general, I mean, are you optimistic about this sort of quasi-lower bound program? The idea that you don't get the consistency of large cardinals, but you kind of prove that
It is
you need large cardinals
necessary.
in order to
In some sense, yeah. In some
produce the
sense, this
result by a certain method.
in some sense this is true. This is true, and this. I mean, once you get to the point in which you get failure of squares,
Right.
you are basically in this domain. You basically can say, I'm starting with some model witnessing this and that. And
Forget the lower bounds.
We can get a lot from Taylor
Forget core model
squares.
theory. Core model theory is just a
It's the
refinement.
same
of
hypothesis.
it.
Actually.
But you want to know is, can you do it with less than this large cardinal? And it says, no, you can't.
yes, yes.
Just
There
to
is,
reverse the consistency implication.
yeah.
Put them out of business.
There is a there is a different question, which is basically saying, well, here we did something which is slightly misleading. So we said the filter extension property enables us to embed a compactness principle into, well, extending filters. But now you can say, well, the filters that you are going to get are extremely nasty, right? They are extremely nasty. They are extremely bad. They are not definable in any reasonable way. What happens if you try to only extend kappa complete filters which are definable using some subset of kappa? Let's say that simply definable in h of kappa plus, right? Very certainly you're going to get something lower. Clearly, subcompact will you can use less than this. Yeah, but what do you need? This is unclear. Might be extremely smaller. Okay. Any more questions?
Don't
I will
worry.
ask my questions later.
Don't worry, you're not going to be put on business. All right, thank you, Yair.